Welcome to Biomechanics. My name is Professor Tom DeLong, and I'll be with you for the remainder of the quarter to teach you about biomechanics, which is an absolutely fascinating field. And you as coaches or even scientists, if we look at it, we need to know as much about biomechanics, mechanics of like classical mechanics applied to the human body. Basically, that's why they call it biomechanics, because it's biological tissue. Now, let's begin with what the cold hard truth is. We look at what the public thinks about it, society thinks about it. The general fitness public and the regular public generally believes in far more comfortable with cerebrally undemanding mantras and fast food solutions than with far more accurate, more complex, and often more successful methods of getting the human body to adapt to stresses so they can improve human performance. And what people do, even in the training industry or even in laboratories and stuff, they will copy programs from other places instead of developing their own and learning how the human body works. So basically, you're becoming an engineer, a technician, because you have to be able to train the human body in such a way that you don't get hurt and you can improve performance. And this applies to everyone who's in this field, whether you're a coach, whether you're a teacher, whether you're a scientist, or whether you're actually participating in some kind of movement, whether it's movements of everyday life or in a sporting event, any activity, you need to know how you move correctly. Because we're so used to looking at YouTube and looking at the internet, because the internet has endless amounts of information that anybody can put information on and say, yes, I'm an expert and all that. So you have to take that into consideration, because you need to learn the science of how the human body works and how it's put together. Now, if you look at the process of gathering all this information that we're talking about biomechanics, you have to look at it in different stages. So once you go to school, you take an anatomy class, take a physiology class, take a biomechanics class, you learn how everything works and everything and how it adapts. Then you have all this stored information in your head. But if you don't have any experience, what do you do with it? And that's the informational stage. So what we want to do with time and experience is go through to the transformational stage and say, this is how we're going to use this information to optimize training for the individual. And that's what it's going to be about. You get a baseline, but then you have to individualize training and people's individualized movement patterns as well. So if we look at the evolution of information, if we look at the screen and see on the left-hand side, we have information. It's a box with all these dots in it. And if you look at each one of those dots is a bit of information, a bit of data. But if you look at them, they're scattered everywhere. If you look at the middle one, that's knowledge, because you'll take individual bits of data and hook them together. They're not all linked, but a few of them are linked together, then others are linked together. But we have them in different stages where we can extract that data and use it accordingly. Now that's knowledge. Wisdom is being able to take the right type of information that we need, that right data, and use it accordingly. Once we've used it accordingly, then we can take other bits of information as well to collectively use it to help train people and learn how to optimize movement patterns for the individual. So if we look at that, what is biomechanics? Well, as we said before, if we look at biomechanics, we got classical mechanics, engineering principles, basically on biological tissues. So if we look at this, biomechanics is divided into two things. One is kinesiology. That's the structure and function of the human body. And we're going to focus, there are like 11 different systems in the body, but we're going to focus on what we call the kinetic chain, the force chain. And we've got the skeletal system, muscular system, and the nervous system. Remember, muscle's pretty stupid. It's not going to do anything until it gets an input from somewhere like the nervous system. But if we look at that structure which is the skeletal system, muscles on top of that, and the nervous system controlling it, that's what we call anatomy and phys, or structure and function. You have to learn how the structure is put together, what material it's made of, how it's going to be stressed, and how it functions. On the other side is physics. What we referred to in all the categories of mechanics, we're going to use rigid body mechanics on deformable material. So the human body is deformable material, but it's able to take a lot of stress. But we have to know how to apply those principles accordingly to make sure people don't get injured when we're trying to help them improve their performance. Now, once again, we look at the breakdown. We have to learn kinesiology and biomechanics. We can learn them simultaneously along with the training regimens that you're going to be using for whatever activity that your athlete or you want to participate in. That structure and function, the types of motion that you want, and the forces that cause that motion or could impact our performance. Next, you perform assessments. Does the data match the individuals or the lifters? If you're having somebody in the weight room, you need to see how they're put together, what their body type is, the length of their segments and all that, how the forces are applied, and how can you optimize the training and the forces to make sure the individual structure is functioning correctly. And we can apply this to every movement we do. And from McGinnis's book from 2013, we can use the do-I principles. Do I have the information to be able to describe the perfect technique for whatever motion? You have to be able to observe it. Do I have the information to observe that correctly? Do I have the information to evaluate it correctly? And then do I have the information to instruct that individual how to move properly to make sure all the forces are in the right places? Additional analysis tools could be looking at key movement patterns. The NHM is normal human movements. We push things, we pull things, we walk, we run, we skip, we jump, we squat up and down, we lift, we carry, bend, twist. All those put together, and we can do them in combinations of that. All those movements applied to an activity is called a skill. Every skill that we do has a basic technique, but also remember too that every skill has a basic technique, but what about the variations of those particular types of skills? So we have to look at that too. So we have to look at the fundamental technique and that variable of that movement, and we have to see what fits that person correctly. You can't just, that's why I said before in the beginning of the presentation, you can't just copy something from somebody else. You can use that as a guideline how to get started, but in the end, you're going to have to optimize their style of technique in any movement pattern at all. Now, we get a perspective on biomechanics. If you look at the screen, I like to use this as kind of like a joke, but because if you look at somebody that's moving and doing anywhere, it's lifting weights, throwing something, running, jumping, whatever, we see a before and an after. So we look at that and look at that. That exercise and training is simply a mechanical stress placed on the body to which that body will adapt to. So we have to look at how that person's moving and say, that doesn't look right, or that's just ugly. But how can we get them to move better? So that's why I have those two pictures there. Next, let's look at some scientific and engineering ideologies. If you look at the human body, it's the ultimate machine. The pictures there is of the Terminator robot, but the Terminator robot was made to look like a human being and move exactly like that. So if we look at that like a machine, we have a computer system, which is our brain. We have an electrical system, which is a nervous system. We have engines, which are the muscles. We have a frame, which is a skeleton. Structural joints, shoulder, elbow, hips, knees, all those joints, movement's going to be caused there around an axis of rotation. We have a cooling system, we sweat. We have a transmission. We can actually make our bodies be on automatic. If something's coming at us, we move automatically, or we can go really slow, like when you're trying to drive a car. You learn to drive it, manually, and then you're on automatic pilot. You can just drive itself. We have a circulatory system, and the big thing here is we have sensors and actuators. So your body, whatever part of the body is, there's sensors and actuators. A good example is you put your hand on a hot stove. It's going to sense this is too hot, then it's going to pull away. But your body is filled with these. And every system we have has all these sensors and actuators. But if you look at this, you can see that we actually are one of the most amazing machines ever developed. So this screen is going to be a little different. So on the top line, we have on the left hand side, we have the Saturn V rocket. That's what took us to the moon in the 1960s. And one of the reasons why I have this on there as well too, because if we look at it, that was developed with a slide rule and blueprints. We didn't have computer design then. We had to do everything by hand. On the other side is the new space launch system that's going to help us go back to the moon and maybe to Mars. This is a much upgraded version of the Saturn V. But the reason we have it on here, because these are engineering marvels. If you look at the structures, long and linear, but if you look at the bottom, at the very bottom of these launch vehicles, the base of it has to be really, really strong to be able to withstand the forces that are coming down on it for the other stages. If we look at our human body, it goes from really thick to very thin up at the top because our legs have to support everything else. And we're built just like these launch systems because we have to be able to handle any type of stress that's thrown at us, from vibration to any kind of pressure, any kind of external force that could cause the joints in there. The joints are structured with all the materials they use. They're put together and welded or riveted, but they're put together. You don't want any of those joints to fail when you're in movement and when the engines fire to produce thrust. Now, we also have two pictures of architecture here. One's just like a storage building, and the other one's your house. If you look at that, our bodies are like this as well too. You can apply mechanical and structural engineering principles to these things because on each of them, they have structures that are vertical and horizontal that are joined together as joints. But when you put all that pressure on there on a foundation, you have to make sure they're secure enough to be able to hold the load. If you look at the human body, it's the same way. But most of our joints are regular joints that move, diatheroid joints. So there's movement there. But we also have other joints too that are structural joints, that are sutural joints that don't move. So they have to be able to protect whatever it's holding in there. So if you look at the engineering principles that we use for rockets, we use for buildings, it's the same for the human body. Because we have to make sure that the tissue is able to handle the type of stress we impose upon it. Now, this one is a block diagram of the body, but you can see how it goes from the bottom up. There's a vibrating platform. So if you look at that, the vibration is going to go all the way up through the human body. But if you look at that, there has to be shock absorbers or struts to be able to absorb that vibration or any type of stress that's on there so the body doesn't get injured and is able to take that type of stress. That's from training. And if you look at this, it's a lot like the buildings and it's a lot like those launch vehicles we just talked about. Therefore, you have to consider yourself an engineering scientist for the human body. You're a technician. You're a mechanic of the human body. Our goal is to increase performance. I don't care if it's from activities of daily living or some kind of sporting event. You still have to know how this machine works so it doesn't get injured. It can improve its performance and not get injured. Or think about it. If you know how your car works, you get it maintained every now and then to make sure it's running optimally. But you have to make sure that car is built for what you wanted, whether it's just taking kids to school or it's going up and down mountains. It has to be able to take that stress. So that's why you have to consider yourself an engineer to make sure everything is going to be able to take the stress that you want. How do we do this? Well, we have to have knowledge of all the systems in the body and all the elements, the parts in those systems. And that we have to know the forces on every part in every system. So if you look at the human body, what's the material like? What's it made out of? What's it for? What's its purpose? And how can we train it? How can we load it accordingly to keep performing on a regular basis without injury? And from that, you have to do a diagnostic. You learn the parts, learn how it moves, everything, but you have to keep doing a diagnostics test on a regular basis to make sure all the parts are working and they're not broken. You have to fix the underperforming part if something's wrong in a particular system to help improve the machine's performance overall. Then you have to do a reevaluation as well. So why is biomechanics important? As we've said, we have to learn how the human body is meant to move. Which movements do we need to avoid and why? Because there's a lot of different movements that people do out in activities, whether it's training in the gym or training on the field or just walking, picking up groceries, whatever it is. If they're in the wrong position and a wrong movement pattern, that could increase injury, but so you want to try to avoid it. So you have to look at mechanics versus technique as well. You look at the technique to make sure are all the forces in the correct place on that tissue to make sure it can perform the movement as it's supposed to without any excess stress. If you do not understand these fundamental principles of force application for everyone's movement or their training, this could be really inefficient and increase the potential for injury. Now, the goals of biomechanics, first and foremost, it's for injury prevention and rehabilitation. That's why we do the individualized techniques, whether it's running, jumping, picking a box off the floor, putting something away, or just, walking up a flight of stairs. And if you're going to train, you have to look at the equipment uses to reduce that amount of injury. In other words, they have to be able to use the equipment accordingly. The next would be performance enhancement. The technique of everything that we do, every movement pattern, whatever, even, like I said, activities of daily living or in some kind of activity or performance. And that's even for all the equipment we use too. Think about all the body parts are pieces of equipment that need to be maintained and able to take the stress. And that's for training improvements as well. So how do we define the categories of biomechanics? One, kinesiology is a study of human movement. The next would be rigid body mechanics. Rigid body mechanics applied to the structure and function of the human body and how does it move. So we can do that. We can optimize the forces, and all forces is anything that causes or tends to cause a change in motion. So we have motive forces, propulsion forces, resistive forces, rotational forces, and even rates of force development, whether it's against the floor or pushing an object. Next is kinematics. That is motion independent of the forces that we have. And the next is kinetics, the forces that cause motion. And remember, there's different types of motions too. So we need to know how we are put together, how we move, the forces which influence those movements, and that's the internal forces on our bodies versus the external forces. If we optimize those, we can increase performance and decrease the risk of injury. So like I said, we just looked at kinesiology, we looked at motion. All motion is the displacement of an object from one point to the other. The types of motions we have are straight line, linear motions, curvilinear, rotary motions, and if we combine all those together, is what they call general motion. That is normal human movements. So if we use kinesiology to analyze correctly, you should have knowledge and understanding of all the body system, particularly the kinetic chain. And we have to be able to teach others how to move correctly and know how and what to do in relationships to all the categories of strength. So even learning a skill is considered a category of strength. And why specific exercises and systems of training should be used, or even just how to properly pick up a box off the floor. We must look at what is moving. Then we must identify what system is involved in any type of motion as well. Remember, and all a system is a body or group of bodies that are being examined. So if we look at the human body, it's one whole system, but like the arm is considered a system. If it's attached to the shoulder blade, it's called the shoulder girdle, made up of different parts. So the next one is physics. Yes, we have to learn physics. A lot of people think, well, why? Well, yes, really, it's really not that bad. Why is it important? Well, you have to be able to apply physics, and all physics is motion, or is mass, energy, motion, and forces. And if you think about that, that's what happens in our human body. And you have to be able to explain it correctly. Because if you look at what Einstein said, if you can't explain it simply, you don't know it well enough. And for a lot of you out there that are coaches, you have to be able to tell people how to do this movement correctly to make sure they're doing it right and decrease the risk of injury. Now, for rigid body mechanics, we have the internal forces that are inside the body. We have active and passive forces in the body. Then the external forces are produced outside. Gravity, which your body weight is some kind of external load. Fluid resistance, air, wind, water. You can use elastics, like elastic bands and springs. But remember, we're balancing both forces for producing what they call eustress. That's good stress applied to the body to get the right changes that we want. That's what biomechanics is really all about. So premise one, the primarily physiological effect of exercise, both good and bad, are in direct response to the mechanical stress we impose upon the body or system. Distress means bad stress, so you're going to get an injury. Good stress means everything's in the right place, the forces, and stress, so it gets the right changes that we want. That's adaptation. So in premise two, in order to facilitate the proper adaptations, we must understand internal versus external forces. How are they applied? The magnitude of the force, how much? Direction of the forces, the point of application of that force as well, the line of action of the force. As you apply force, what direction is it moving in? How fast you're moving? What about the range of motion of the system? We talked about the body having a lot of joints and everything that are very movable. What's the range of motion at that joint and the system that it's attached to? How does it move? Is it proper range of motion? How the tissue of the body adapts, how the tissues of the body will adapt to these forces applied to it. So premise three, understanding and implementing biomechanics is essential in all aspects of training. We assess these persons, we design a training for them, we implement or instruct them how to move correctly, and then we reassess. So it's a circle, but it's ongoing all throughout your life, how to do things correctly without getting injured. We analyze that person, optimize their techniques, which will help maximize their performance and minimize the risk of injury. So the concept of mechanics, three fundamental units: time, distance, and mass. That's what we're looking for. And it's all about power output. What is power output? Most people think it's explosiveness, but actually power is nothing more than how much the rate of doing work, how fast are you performing work, and that's force times distance. So basically, power is basically force times velocity. So you can be going really slow, have a low power output, or you can be going fast with a lot of force. That's a high power output. So you need to understand what power is and how it relates to force production. Qualitative versus quantitative. Quantitative, it is how fast are you, or quantitative, how fast are you going, or how far are you going, or how much load that you have on the body. Qualitative is looking at non-numerical descriptions like good versus poor, long versus short, heavy versus light. That's qualitative versus quantitative. Now, the great thing about biomechanics is you can have applied biomechanics, but you can use the quantitative values if you want to actually look at specifics in any part of that movement, whether it's velocity, force, acceleration, whatever. You can actually measure it. But for the most part, most people just need to know the applied aspects. So if we look at statics and dynamics, we know statics is not moving. That's Newton's first law, the law of inertia. Dynamics is a study of systems which acceleration is present. And that's Newton's second law, the law of acceleration. And it's all about force. And we said before, it's anything that causes or tends to cause a change in motion. It could be a push or a pull. It could be a rub, which is friction, a blow or an impact, or what we deal with all the time is wonderful gravity. We always have gravity down here, so think about that. We have to be able to hold ourselves up. Everything has to be firing correctly just to keep us upright. And then when we add motion to that, it gets even worse because look at all the stresses you're applying over a period of time. One of the things we're going to use too are vectors. All vector is a representative of what a force is. They look like arrows. So the longer the arrow is, the longer the force is applied. The thicker the arrow is, it's going to be the magnitude, how much force. And we call them vectors because it has magnitude and direction. And we have to look at the modes of application as well too. Compression forces, tensile forces, pulling apart, rotational forces or torque, shear forces are combinations of all those. So once again, if we look at here about how to load the body, the skeletal system and the muscles that get stronger to help it move, it's the same engineering principles that we looked at to build a house or have a rocket. So here's a picture of that, the compression forces, shear forces. Look at the compression forces on the spine. That's what the spine, the vertebral column is built for compression forces, but it also rotates and flexes, 6 degrees of freedom. So you have to know when you're doing something where all these forces are. You have to be able to see those forces. So if we look at the typical force time curve, it's an overview of the maximum rate of force development. How fast are you producing force? In this particular diagram, the dotted line is the resistance you're trying to overcome. So in the first milliseconds of that movement, you're trying to overcome that external load. So you have starting strength, acceleration strength, then you'll have the rate of force development, then you have your explosive strength, which is your max rate of force development. So this line won't look like this, it'll actually be a steep line. The slope of the line, if you're on a force plate, will tell you how much force you're applying to that. You can use force plates to do that, but we'll talk about that during the quarter about what this is and how to increase it. So we put it all together, assessment, optimization, and that maximizes and that minimizes injury. That's what it's all going to look like. So you must see all these forces. That's internal and external forces and their effects on the body. So I hope you liked the class. If you got any questions, ask me. More than happy to answer. So let's open up that great dialogue and let's learn how all those forces affect the human body, the greatest machine ever developed.